how magnetism links with electrical currents. So magnetism is actually the result of electrical currents, and we're going to explore that. And we're going to look at the direction of a magnetic force acting on an electrical circuit. So magnetism, we've known about it for a long time. The ancient Greeks would look at it and they noticed that there were some rocks that attracted metals. They thought they had mystical properties. Okay? But they did find that you hang it from a piece of string, these stones would always point towards the North Star. So that's why we name the ends of any magnet the North and South poles. What we now know is that magnetism is a field which extends into space. So magnetic materials will align themselves with this field. And what we do is we draw the field running from the north to the south. That's just a convention. Okay, so we can see this field if we look at iron filings. Okay, we can scatter them over the top. We can see these field lines and how they line up. If we're drawing it, we see that we draw them going from north to south. So these field lines come out of the North Pole into the south. So for about 2,000 years, magnets, all they thought was weird rocks, most likely magic. Then in 1820, a guy called Hans Christian Ørsted was playing with this useless thing called electricity. That's what they thought at the time, when he noticed something strange. This is what he noticed.
In 1820, Danish physicist and chemist Hans Christian Ørsted was setting up materials for a lecture. His materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a dilute acid solution, and a wire held in place here by a set of clamps. Ørsted and other scientists of his day knew that when a wire was connected between the positive and negative terminals of a battery, electricity would flow through that wire. Electrons actually move from negative to positive. However, the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it here, using red particles. Back then, scientists still had much to learn about electricity. Preparing for his lecture, Ørsted made a very important discovery about the phenomenon, quite accidentally. Among Ørsted's scientific paraphernalia was a compass, its needle, of course, pointed north in alignment with the Earth's magnetic field. Ørsted happened to place the compass near his battery and was startled to notice that the compass needle moved. As Ørsted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's magnetic field. As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current, as shown by these blue lines.
So basically, this guy Ørsted showed that electrical currents produce a magnetic field. Michael Faraday, who you've probably heard of, demonstrated later that they also feel magnetic forces. Okay. So between these two current discoveries, what they found was that electric currents exactly mimic magnets. So they called it electromagnetism. So the magnet and the electrical current, they behave in exactly the same way. Okay? A current is a magnet. So when electrical current is flowing through a wire, there is a magnet there. The force in a magnetic wire is at right angle to the magnetic field line, north to south, remember, and the current itself. Okay? So there's a force, and you need to think in 3D here. There's a force which pulls on the wire, there's a magnetic field, and there's a current. Grab your left hand, stick your left thumb up, your forefinger up, and your index finger out to the side. And if you want to, you can shout freeze FBI. Could look like that. Okay? This is how we're going to think about these 3 dimensions, and it helps us. So the force, F, the current, I, and the magnetic field, B. So if we know any 2 of those, we can work out the direction of the other. So in that first one, you need to twist your hand around. You need to remember that you've got to go north to south. And we would expect, therefore, that the wires would move down because the force is pointing down. So line up your fingers so the current's pointing in the right direction. Your pointer finger is going north to south, and you'll find your thumb is pointing downwards. Same thing with the U-shaped magnet. You should find you get a force going upwards. If you have parallel wires, they would either attract or repel, depending on whether that force is moving them in the same direction or different directions. Okay? That will depend on whether the current is flowing through them in the same direction or in opposite directions. So the key things to remember: all electric currents produce magnetic fields around them. An electrical current experiences a force always when it's put in a magnetic field, and we can use that left-hand rule to figure out which way it's going to move.